So a couple final pieces to go over with proton NMR, and once we finish that, it's going to become time to start putting all of this spectroscopy together. So the first of these pieces is to talk about integration. So if you've taken calculus at all, this is a term you might be familiar with. For those who've taken Calc 1, integration is largely the opposite of derivatives. But what information does integration give us? So integration is really, it's defined, or one of the ways it can be defined as the area under a curve, if we've drawn a graph of our equation. And so if we look back at any of these NMR spectra that we've seen so far, and we look carefully at them, you can see these peaks aren't just lines. There's actually space under them. And so we could calculate the area that's under these peaks. Now, that's not something we're actually going to sit here and do the math for. That would be incredibly tedious and time consuming, especially given the shape of some of these peaks. But fortunately, the software that we have for NMR spectroscopy does this calculation in a matter of, not even a second or two. So what does it tell us? And why would we care? Well, the area under each peak it turns out is proportional to the number of hydrogens it represents. And this is only true for proton NMR. You can't use this for carbon NMR. Now, the values are all relative, and probably the biggest problem with integration, and this is something you'll see when you're in the lab and you try and use this, is that the computer doesn't know how many protons a peak should be. So the first time you integrate a peak in a new spectrum, it's going to automatically set that peak to an integration of 1. And then every other peak will get given a value relative to that. So often, and this is something we'll go over more in lab, but there's two straightforward ways to fix it. One is that if you know how many protons any one given peak in your molecule represents, you can use that as a reference, assign it, and then everything will be calculated relative to that. The other way is if you know the total number of protons in your molecule. Then you could integrate all of your peaks that you need to integrate that are part of your compound. And after you've done that, you would just tell the software that there should be, instead of these peaks adding up to 7, they should add up to 15, and it'll scale accordingly. I also want to briefly talk about what's known as a coupling constant. So a coupling constant is, for example, if we have a doublet, we could measure the distance between the two peaks in the doublet. Or if we had a triplet, we could measure the distance between the first peak and the second peak, or between the second peak and the third peak. And so the coupling constant is this distance. So it's the distance between the peaks in a splitting pattern. And coupling constants are almost always measured in hertz. So that's really all I want to say about coupling constants today. But when we get to alkenes, we'll come back to this idea of coupling constants. The final piece I want to talk about before we start looking at more spectra are acidic protons. So carboxylic acids, when we started this section on proton NMR, we said this proton in a carboxylic acid is very diagnostic because it shows up, 11, 12, 13 ppm. And in a proton NMR, it's the only thing that shows up that far. Except for one problem. What do we know about carboxylic acids? Well, they are in general acidic. In addition to being acidic, we know that they're polar. So a lot of times the common solvents that you use for NMR don't work anywhere near as well for carboxylic acids. They end up not being soluble. And so if you use a very polar solvent, for example, if your solvent has acidic hydrogen such as D2O, deuterated water, your deuterium in the water, your solvent, can exchange for the hydrogen on the carboxylic acid. And so as a result, you get this compound instead, which for all practical purposes behaves the same. But for NMR purposes, that's different. That's a different group. The NMR won't see it. And so if you have a carboxylic acid, you might start and you think you're going to see this peak out at 12 ppm. And you take the spectrum and there's nothing there. Why is that? That's because it may have exchanged away with the solvent. So at this point, what I'd like to do before I send you off to do some practice is for us to do some practice on the types of problems that we're going to be able to do now. And those types of problems are problems where all I need to give you is the spectra and a chemical formula, and you should be able to come up with what the compound is. We could even at some point in the future go even one step harder, and I could give you, instead of giving you the chemical formula, I could just give you the mass spec instead. But again, the goal here is going to be to identify compounds just based on their spectra. And at the end of Organic 1 lab, that's actually going to be our final lab activity in that course. Is that at the end of Organic 1 lab, I'm going to hand each of you a compound, and basically you'll take a lab period and go all around the lab doing different things that you've learned to try and figure out what it is. Alright, so here we have our formula, C10H14O2. So if you may notice I'm trying to suggest a first step, calculate out your degrees of unsaturation. And we get a total of 4. As we've said previously, the first thing that says to me is aromatic. Now let's look at our IR. So first I look out here above 3,000. And what's there? Well, nothing. So I can be reasonably certain we don't have any alcohols. I'm also going to look in this region, 1700. Again, there's nothing there. So I can say with a pretty high degree of certainty, no carbonyls either. But we've got these two oxygens. What does that mean we probably have for a functional group? To me, that says there's a good chance we have an ether, because an ether is something we don't see in the IR spectrum. And it's really all that's left, because we've already said we have no alcohol and no carbonyl. All right, if we go on to the proton NMR, something interesting happens. And that's for a molecule that has 10 carbons, 14 hydrogens, there's only 3 peaks. What does that suggest to us? Well, I know what it suggests to me is that it tells us our molecule is probably symmetrical. Now, what other information do we get? Well, the first thing is this peak right here around 7. That's right within the aromatic region. So our thoughts that we had an aromatic based on the degrees of unsaturation looks like it was pretty accurate. Now, the remaining peaks are a quartet and a triplet. And this is a pattern that you should get used to seeing. If we have a quartet, that means it's next to 3 hydrogens. Well, our triplet down here is pretty close to 1 ppm, which suggests to us that this triplet comes from a methyl group at the end of a chain, such as this one, that's causing the splitting to a quartet. Well, if this CH3 is represented by this peak, it's triplet. A triplet means that it's adjacent to 2. So when we see this quartet triplet pattern like this, it's usually a pretty good sign that we have an ethyl group. Now, where do we go from here? Because we've identified an aromatic, so that's 6 carbons. We've also identified an ethyl group. But the other piece we can still get is that the ethyl group has to be attached to something electronegative because it's showing up at 4 ppm. And an aromatic ring just being attached to an ethyl is not nearly enough to take it to that high of a chemical shift. What is? Well, we have these 2 oxygens. So if we put that oxygen there, and then we have an R group on the other side, that will account for the chemical shift, and it also accounts for the fact that we didn't see an alcohol or a carbonyl, and said that we probably had an ether. So we're almost done, but we've still got 2 carbons to account for. We've used 8 of the 10 carbons so far. Well, if I go back to this aromatic peak here at around 7 ppm, one of the things I notice is that it's a singlet. Because it's a singlet, that means that all of the hydrogens in the aromatic ring have to be equivalent. Well, if you think about what's left from our initial starting conditions, we still have an oxygen, we still have 2 carbons. The only way to make all 4 hydrogens, or all of our hydrogens in the aromatic ring equivalent, is by making it symmetric. So this would be the structure that I would propose given what we have here. Now, we haven't even looked at the C13 spectrum, but what I'm going to use the C13 spectrum for is to say, does it make sense? So there's our compound again. We know that these are equivalent, and they fit methyl at the end of a chain, 10 to 20 ppm. We have a carbon at 60 ppm, very likely next to an oxygen. We have an aromatic carbon almost out at 160. So that's likely to be attached to something electronegative, which is those 2 carbons. And finally, this is an aromatic carbon. All 4 of these are equivalent. So we didn't need the carbon spectrum to determine what the structure was, but as you can see, we were able to use it to confirm. So let's do one more of these, and then I'll leave you to practice some. All right, C9H12O. We can calculate our degrees of unsaturation. Again, we get 4. So again, that suggests to us that there's a good chance for an aromatic ring. Now we have an oxygen in this compound, and we have this peak right here. Now, what is that? Well, that peak looks like it's not quite strong enough to be an alcohol. But it's a little too strong to be an amine. But those are really only the only 2 possibilities. So which one do you think it is? An alcohol or an amine? Now hopefully all of you said alcohol, because there's no way that it can be an amine. How do we know it can't be an amine? Now you may laugh at the answer I'm about to give, but I've seen enough wrong answers like this over the years that I have to point this out. It can't be an amine because there's no nitrogens in this compound. So from our IR spectrum, we know the formula, and we know that we have an alcohol. Now the alcohol peak is sometimes tough to see, but you can see it's right there. All right, the next peak I want to look at is this one by 3 ppm. It's hard to tell from looking at this, but it is a septet, and this peak is a doublet. Both of these peaks are also doublets. So if we have a septet, the only way, I shouldn't say the only way, but 99.9% of the time, a septet, because that means being adjacent to 6, the only way to get that is with 2 methyl groups, which means we have something that looks like this. So this CH is next to 2 equivalent methyl groups, gives us a septet, whereas the 2 methyl groups are adjacent to 1 and give us a doublet. This is also another good example of integration, though. Notice the septet, which only represents one H, is a very small peak, whereas the doublet, which represents 6 hydrogens, is a much larger peak. So right now we know we have an OH, we know we have an isopropyl, and we know we have an aromatic ring. Now we just have to put them together. And there's 3 ways we could do that. They could go next to each other. They could have 1 carbon in between. And they could have 2 carbons in between. So this middle one has this peak here in the middle, which would be a singlet. And given that these are both doublets, we know that's not correct. The one up on top would give us a doublet here and a doublet here. So that one's still okay. The one on the bottom would also give us 2 doublets. That doesn't help us. So we're going to have to go to the carbon 13 to pick the correct one between these two. But with our carbon spectrum, we will be able to come up with a final answer. So in both cases, we're going to see these 2 peaks out here to represent the isopropyl group. That won't change to any significant amount. But here's where we get a difference. For this compound, and we're going to go back because I've made a mistake here. These 2 are not both doublets, and I'd like to correct that. Here we'd have a doublet. This one is adjacent to 2 that are not equivalent. Doublet of doublets, same here, and this one is a doublet. What I was saying previously would have been true if these 2 groups had been the same. Because they're not, these 2 hydrogens are not the same, and we get 4 different hydrogens. So because of that, and the fact that we only have 2 peaks here, we know that this cannot be the correct structure. So finally then, is this molecule consistent with what we have? This would give us 1, 2, 3, 4 aromatic carbons, and that's what we see. So at this point, you should get out in-class exercise number 13 and start working through some of those spectroscopy problems.